So just to thank a few people who worked with me. This work was supported by L'Oreal, cosmetics company, and I worked with several excellent scientists in that company, and as well with several excellent engineering students in my university who did most of the real work, as we know. So this is about what people call split ends, okay, which is a very common problem that people have, especially if you have hair which is quite long, or if you treat your hair by coloring it or other things like that, then you can get this effect. And really, of course, it's simply a crack propagation problem, because it's a crack which is propagating longitudinally along the hair strand. So, you know, I was asked by this company to look into the fractal mechanics of this problem. Okay, oops, did it again. So a couple of things you need to know about hair. It's a fibrous material, and it's extremely anisotropic. And we don't really know how anisotropic it is, because nobody has managed to test it in the direction perpendicular to the length, as you can imagine. But I'm guessing from various work I've done that it's probably something like 1 to 10 as regards Young's modulus, and maybe something like 4 or 5 times weaker as regards the strength in that direction. But certainly it's in the same way as a unidirectional fiber composite, it's very anisotropic. And the other thing you need to know is that it has a very high strain to failure. We heard this morning from Alan Pelton about nitinol and how it has this phase change. Well, the same thing happens in the keratin that this hair is made of, but it goes through a phase change which allows it to extend enormously at something like 50% strain. Whoops, something like 50% strain is possible before it finally fails. So you have this long, looks like plastic, but it's not really plastic, it's changing phase. But anyway, the result is that because your hair is extremely flexible in that sense, then if you put it in a microscope, you can see sometimes that your hair strands literally form knots like this, and very often they bend over each other and form these tangles and knots, which are so annoying when you're trying to brush your hair out. Okay, so it's for these reasons that we get, you know, particular behavior of hair. And there's been a theory around since the 1970s that suggests that the reason that you get splits in hair is because of the high shear stress in bending, which we're all very familiar with, right? So if you take a hair strand and you bend it, of course, the main tensile bending stresses are top and bottom, but of course you also get a longitudinal shear stress, and because of the great anisotropy of the hair, it may well decide that that's the way that it would like to fail. Same as we heard also this morning in this room about failures in composite materials. So that's the theory, but it was never really put on a proper theoretical basis, and crucially, nobody really designed an experiment where we could create the splitting in the laboratory. Okay, which is really what we've been doing. So we devised some new tests. So this is just a simple tensile test where you've got a single strand of hair and you pull on it. Well, lots of people in the past have done that. That's easy. What we did next then was we took 2 hairs and we looped one hair over the other, right? So it's kind of like a link in a chain, right? And then you can pull on that, which is interesting, and that's great. But more interesting is you can hang a weight from the lower strand of hair, and then you can move the upper strand through the loop, okay? So now every part of this upper hair is passing through that stress concentration of the loop, right? And we propose this as a kind of a simple simulation of what happens when you comb your hair. You try to comb it, you feel a tangle, and then you push on that tangle, and you eventually propagate it right the way down to the end of your hair. So if we do that just a single movement, we call that a moving loop test. What I'm going to talk about today is the fatigue version of that, where you cycle backwards and forwards, simulating a lot of brushing strokes. And so it's, say, repeatedly moving every part of this upper hair through that really very severe stress concentration, because this is what it looks like when the loop is closing. If you apply more and more force, we can get almost a complete closure. So you've got strains there getting close to 50% strain if you work that out. And that happens quite at loads which are quite a lot lower than the failure force. So even when the force is down here somewhere, we've already got that loop quite nicely closed, and that's the conditions under which we then do the fatigue test. Okay. Now, so we took two hairs from two different subjects, right? The red one is just a stress strain curve. The red one is from a person who suffers a lot from split ends, okay? And the black line is hair from a person who doesn't suffer from split ends at all, okay? So we were hoping to see, obviously, a difference between those two. In the simple stress strain test on the strand of hair, longitudinal pull, as you can see, there's no difference at all. That's just an example, but even statistically, they seem to have the same tensile longitudinal strength, right? But then when we did the fatigue test, so this is one example of our fatigue results, where the weight that we're hanging is 14 grams, which, to give you an idea, that's about 20% of the weight that we would have to apply to break that hair in a single pull. Okay, so it's a lot less than the effective strength of the loop. But if we do that and then we cycle, then we get failures for the what we call the low quality hair. That's the hair that splits. We get failures in about average 200 cycles, whereas with the good hair, the control, we get failures in about 500 cycles. And yes, there's quite a bit of scatter, but statistically, there's a significant difference between those two. Okay, so here for the first time, we have a test which can actually tell you whether your hair is likely to split or not, or at least give us some numbers on it. But what was even more interesting, and this is where we get to the crack paths part of the talk. Similar results, that's just at a different applied stress, but same idea anyway. What gets interesting from the crack paths point of view is that the failures were different, the crack propagations were different. So in the low quality hair, the split ends type hair, we got these very long splits running right along the length of the hair strand. So we start off with a length of hair, our test length is about 40 millimeters. And after a while, we look at the experiment going on, and instead of having one hair, it looked like we had two, because the hair had completely split from end to end right the way along. Whereas, let's take a couple more pictures of that. And, you know, if we stop at an earlier stage, you can see these splits starting as initiated cracks in the center of the hair. And then sometimes, sometimes they don't go all the way. Sometimes they kind of make their way out to the surface at some point and break, and you get a more complicated appearance like that. But anyway, in this hair, we could get these long central splits. Whereas in the other hair, the hair that was not a split end sufferer, we never got those splits. But actually, we got a different type of split, and this was a bit more difficult to discern. Looking at the final failures is a bit of a mess. This is an SEM photograph of part of one of these hairs after it's failed. And you can see what happens for one thing is that it curls up, all right? It's a bit like, you know, when you go buy a present in a shop and they put the ribbon on and they get scissors and they roof like that, right? And so there's some residual stress that's causing that curl up, which makes life a bit complicated. And there's multiple damage events obviously going on this thing. But by doing interrupted tests, we could work out that what's really happening is this, that cracks are starting on the surface and they're propagating in at a very shallow angle, but gradually propagating in here as it happens to there are two. So we're kind of getting multiple initiations of cracks from the outside of the hair, gradually making their way into the center, and then maybe then there's some kind of failure event that they make their way out or whatever. So this is the difference. They're also a kind of split, but a different initiation point for the splits. So that's kind of where we are experimentally. At the moment, what I'm trying to do is develop a theoretical model that captures all this and hopefully can predict it. But as you can imagine, the stress analysis is quite complicated, right? We're just making a finite element model of that. Actually, we haven't done that yet, but you can see that what you've got is a bit like a kind of an extreme three-point bending, really. You've got one hair coming through here, radius R. You've got another hair bent over it. So in the case where the two are the same, then R is equal to R. So you're pulling on the end here, you've got a reaction force. So this is seeing very high strains in a kind of a three-point bending mode, and so clearly there's also going to be a lot of longitudinal shear up there. But it seems to me there's a kind of a competition going on here. One possibility, and this seems to be what's happening in the low-quality hair, is that the cracks are taking advantage of the shear stress in the middle, which is relatively small, but it allows propagation in that weak direction, along the longitudinal direction. But a big issue, and this is the kind of thing I'd like to discuss with people during this conference, actually, because I know I have a lot of good experts to talk to here. One of the issues here in trying to predict that propagation is that, of course, you also have a very big compressive force there, because the direction, the application, the external forces is such that any crack that's trying to initiate and propagate here is being opposed by these forces that are clamping that crack back together again. So we need some kind of multi-axial criterion for describing the propagation of that crack. And then in the other situation that we talked about, with the tends to happen in the normal hair, we seem to have cracks initiating on the surface, but what they don't do is they don't propagate straight across. They always deviate sideways at a really quite a sharp angle, and so then you have a kind of a complex situation there, where you've got a changing mixture of tensile and shear stresses, and again this compressive clamping effect at the end. So anyway, it seems to me that the bottom line, the hypothesis that I'd like to prove, is that the reason we get different behavior, the reason sometimes you get split ends and sometimes you don't, is because of the degree of anisotropy, right? That you have the two hair types here, as I showed you, have the same tensile strength longitudinally, so that's not changing. But what is changing is the strength in the other direction, in the transverse direction, which is maybe getting weaker in some types of hair, and therefore encouraging that longitudinal splitting phenomenon. Okay, so that's about it. It didn't take too long. No. So what we have done is we've devised a test. So the company are very pleased with us, because we now actually, for the first time, have a laboratory test where you can compare my hair to yours, but not mine, because it's not long enough, actually, but compare different people's hair, and you can study the effect of bleaching and other treatments which people apply to their hair, and these products which are supposed to repair your hair and stop this from happening. We haven't got to the point of doing those experiments yet, and if we ever do, they probably won't let me tell you the results, but anyway, it's all possible. What we didn't do, you might have noticed, is we didn't actually generate split ends, because it's a constraint of our test that the split happens in the middle of the sample, because we're clamping the ends. So we need to maybe work on that if we want to be a little bit more realistic. And also what we didn't do yet is to develop a theoretical model. I'm very much hoping to get into discussions with people during the week about what that model would look like and what kind of criteria we need to apply to account, especially for these two difficult aspects, the extreme anisotropy and the effect of these compressive forces on a crack which is in a kind of a mode, otherwise a mode 2 crack, with this compressive clamp. Okay, that's all from me. Thank you very much.